All right, did just post the link tonight, 9 p.m. Central. I will be live streaming here on Zoom. Hearthstone. I'm guessing I'll probably be Diamond to Legend ladder climb. I played a little bit today and I'm already Platinum 9, I think. So we'll uh, get to a world record and or get to a world ranking and then maybe play some interesting decks from there. So if you want to jump on Zoom and heckle me, 9 p.m. Central tonight's the time to do it. I'll also stream it on YouTube and put the video up if you're interested. But feel free to come and go, stay for as long as you want. I was going to sit here and do it anyway, so I figured I'll just be on Zoom and do it and stream. All right. I'm sharing my screen, right? All right, so homework for today was to look into Linux kernel modules and how they work. So what can you tell me about these? What did we find out? By the way, if you see me looking up, it's because you're on my screen up top here. So what's a kernel module?
It's a way to easily add to the Linux kernel without having to rebuild the whole system.
Okay. So what are some what are things we might add to the Linux kernel? What's an example of those kind of things?
I mean, I saw some really basic ones that were as simple as printing something out to the screen, and then maybe some more complex ways to do something in like a more efficient way or something like that.
Okay, so we're going to be looking at it through the lens of of drivers initially, but the reality is we talked last. We've defined a driver in here already, haven't we?
Yeah.
Okay. Oh yeah. So these are just pieces of software that do something. So as Noah just pointed out, this could be a piece of software that makes a cool new expensive graphics card work, or it could be a stupid driver that just makes something print to the screen whenever a certain thing happens on your computer that really doesn't have any real functionality, but it technically is a kernel module. Now Noah mentioned that he said it. One of the reasons why you might want these is so that you can augment the operating system after the fact, after it had been compiled and installed on your computer and that stuff, right? We talked a little bit last time. We talked about I think I was mentioning Gentoo Linux, how it might take a couple of days to compile the kernel once you got through all the errors and stuff like that. So imagine if you were actually writing some addendum to the operating system for something like that. You brought in a driver for something, and you had to add it to the kernel, then you had to recompile the entire kernel. You might have a non-functional operating system for multiple days until you finish debugging it. Where a kernel module builds on top of the idea of something called a microkernel, which I think we started talking about last time. Yeah, so it says, look, we're going to keep only the bare bones, most important, shouldn't change really stuff in the microkernel. And maybe the changes would come with bug fixes and stuff like that. Maybe 2 or 3 times a year you might have actual microkernel updates, as opposed, unless it's some serious crash bug or something. But really keep the bare components of the operating system in the microkernel and have everything else kind of be things that plug into it to make life work. Okay, so that's the idea of a kernel module. All right, so let's think about writing Linux drivers. So this is effective. Well, before we do that, did anybody else find anything interesting to add to the kernel module discussion?
They live in the lib modules folder.
Okay. All right, so that's the location they are in the POSIX hierarchy. So it'd be /lib/modules. So if we flip over here to Ubuntu, here's the top level directory in Ubuntu. And we see we have a lib folder, and inside the
We
lib.
can't see your screen.
Oh, really? Wonder why. Didn't I say desktop 1? You see it now?
Nope. Oh, now we can.
You're seeing the Ubuntu terminal, right?
Yeah, now we are.
Okay. Yeah, so here in the lib folder, we have a modules folder. So here are the modules that are currently, well, here's submodules for this. So these are based on the oh. All right, so these are modules for this particular version of the OS. All right, so this is where they live. And these are the binaries, the actual that run for the modules. All right, anything else you discovered? All right, are we back looking at the writing Linux drivers slide?
Yep.
So 2 ways to write programming a Linux driver. So compile the driver along with the kernel. That's what Noah said we don't want to do. Or we can implement the driver as a kernel module, so we don't have to rewrite the kernel. It's a specifically designed object file. When working with modules, Linux links them to the kernel by loading them to the kernel address space. So when an operating system loads, you have user address space or user program address space, sometimes it's called, and then you also have an address space that belongs to the microkernel. This address space is kind of locked down. All right, so if we were to draw a picture of this, we're going to call this kernel address space. I'll make that relatively small. And then we have, I'm just going to call it user address space. Depending on the operating system, you actually could further subdivide this. So we have our system memory, put that in red. Well, actually, we're going to have system memory in yellow, of course. Kernel address space will be red, user address space will be green. All right, now I put it in red, actually I say for course down here, who cares about that, but kernel address space we want to treat as something special. This is protected memory. All right, why might we have the operating system live in a part of memory that is protected from user applications running in there? Why might, or if you want me to ask it a different way, why might we want to have our user applications running in a different address space than a kernel address space?
Because user applications have the potential to be malevolent.
Okay. And from a memory perspective, like in here, we're going to be writing stuff in C. If we create a user program, so this is Noah's hacker program. All right, so let's say Noah's hacker program, it gets loaded in the very beginning of user address space. And Noah's program is able to, you know, he could write some code to find out what the base address of his running program is, and then he can do some pointer math to start getting into this address space over here and rewriting some bits, you know, storing something in a certain place. Maybe it's a known place in kernel address that would cause a certain thing to break or change the value of some flag that might make a directory readable or writable that used to not be readable or writable, whatever it is. You know, only the most trusted running application should happen inside of this kernel address space. Okay, and we want to lock it down from other things that run outside of that address space, really things that run with other permissions. This is usually handled, well, the address spaces are segregated, but the security to them is usually handled by the who's currently running the application. You've probably seen this before on Windows. If you run a program and sometimes you've been told you have to run it as administrator, something like that. Effectively, what we're saying is that this particular program needs to have access to the kernel space for whatever reason, whatever aspect of the operating system it's having to directly interact with. And you have to give permission for it to run as an administrator because it could cause problems. So you should only run trusted applications like that. You know, if you, I mean, I would think this would be a pretty poorly written virus, but if you open some file, you know, with a really funny name from an email and it opens up Microsoft Excel or something and gives a pop-up asking if you want to give this or if you want to run this as administrator, probably hit no. Because something doesn't add up there is I guess the idea. So with that in mind, that's why most modern operating systems separate these two things. Now within kernel address space, we have our actual microkernel that's running. So there's our actual microkernel. Call that. That's running in there. Now, you also then will load in some modules. All right, and these modules live inside of kernel address space because they have to directly interface with the kernel, but there is a mechanism built into this microkernel. Call this the module interface. All right, so these modules hook into the kernel through the module interface, but it all lives here in kernel address space because it needs to access things dealing with the kernel. And if a user program needs to access some of these things, it's going to have permission or run at an elevated level of security, something like that. All right, so that makes sense, the difference between kernel address space and user address space.
Si, senor.
All right, so be careful. Module code has to operate in the kernel context, i.e. kernel address space. This requires a developer to be very attentive. If a developer makes a mistake when implementing a user level application, it will not cause problems outside the user application in most cases, i.e. this picture. Okay, it's running in user address space. It doesn't matter how bad of a programmer Noah is or how unethical he decided to try to be, because it is happening inside of user address space, it's probably not going to crash the operating system, right? That doesn't mean he can't do other malevolent things, but it's probably not going to crash the OS. So it won't cause problems outside the user application in most cases, but mistakes in the implementation of a kernel module will lead to system level issues, i.e. if you screw up one of these guys, it's all living here inside of kernel address space where the rest of your operating system is running. So if you start overwriting some memory that's important memory, in the best case, you're going to have to restart your computer so the OS can reload itself into memory. In a worst case, you could have a worse problem, let's say. Okay, so a kernel module in and of itself is a specifically designed object file. So we have to follow some very specific rules, kind of compatibility things. We're going to look at some examples of this here in a minute, but think of this as kind of, if you remember back in Java, we talked about interfaces where anything that implements an interface has to implement some certain functions, okay? So the module subsystem kind of has that. It says, if you want to be a module and you want to talk to the operating system, this is how you do it. This is the entry and exit points, all right? So, and then again, it operates in the kernel context. That's our picture here. It lives here inside of kernel address space and is linked to the kernel by getting loaded into its address space, i.e. linked through the module interface to the kernel, which lives in the address space. All right. So naming conflicts. This is actually a real problem since we are living here completely in the kernel address space. All right, so the kernel and its modules represent a single program module and use a single global namespace, i.e. all our variables are effectively global variables. Okay, so in order to minimize the namespace, you must control what's exported by the module. That means don't allow all of your variables that you just need as local variables, don't necessarily export them by the module. We'll see some examples of this. Only export things that need to be shared among multiple things. This is almost getting back to our idea of like a singleton design pattern. Remind me, what's a singleton design pattern? Crickets. All of you know what a singleton is. I'm going to sit here until somebody answers me.
Isn't this something kind of like the you can just store a bunch of codes, like snippets of codes, and then just pull from that one area to have it do a bunch of stuff?
Okay. So I think we're relatively close there. Remind me again, what's a design pattern in general? Let's make sure we have that loaded into our spring semester memory. What is a design pattern? If you had to give me a definition for a generic design pattern, what would you say?
A set amount, or like set rules on how you're going to design something so it's the same every time and it's easier to read / use.
I'm going to say no. You said a lot of words. I don't know if they meant anything. Well, they meant something. I don't think they meant the right thing. So design patterns are a proposed good solution to a common problem, right? Where a common problem depends on what kind of industry you're in. You know, if you are, the common problem could be the example I usually use when I first introduce this is, what's the best way to make a peanut butter and jelly? Okay, so you might, and usually design patterns have a funky name. So you might have your own invented best way of making a peanut butter and jelly, and you name it something funky, and somebody else might do it a little bit differently and they name it something funky. Both of those are examples of design patterns. which is a proposed good solution to solving a common problem. In this case, the common problem being making a peanut butter and jelly. But a design pattern is not an implementation. It's the idea of, hey, this is best practices for doing something. A singleton design pattern is the idea that if you have something that needs to be shared among more than one thing, whether it's a screen in an Android application, or maybe multiple drivers need to have access to something that is shared among them, something like that, it makes sense to put that in a single place that they all can reach. That's what a singleton says. If more than one screen needs access to something, put it inside of a singleton so that they all can access it. So we're kind of exporting global variables, okay? But the warning thing here says that if you're exporting global variables, don't just export every variable. Only export variables that need to be available to other modules of the operating system. Not every single variable that you might ever have. Remember in your very first programming class, I probably said something someday, something along the lines of that in general, actually, it probably was in that class, and then again when we talked about singletons, that global variables are something you'll find in a lot of books is that global variables are bad. We have this idea that having a global variable is bad. Well, having a global variable is not innately bad. Doing it when you don't need it is bad. If you created a singleton and you put a variable inside that singleton because you have more than one place in your program that need to access that same variable, that's considered a good idea. And effectively, that's a global variable. But if you have 20 variables in a program, and only one of them needs to be shared among the other modules in our example here, only export that one. Everything else should remain as a local variable. So we want to make sure that our namespace, where our variables are going to live in kernel space, doesn't get overly crowded with a whole bunch of useless variables. Two problems with that is debugging might be a headache. Secondarily, you could have name conflicts with the variable names if they have the same name. All right, so exported global characters must have unique names and be cut to the bare minimum. A commonly used workaround is to simply use the name of the module that's exporting the characters as the prefix for a global character name. So you might have something like, NVIDIA GPU underscore my global variable. That would be a way of having your a variable named my global variable not having naming conflict with some other programs my global variable because it belongs to a different module and you named it with the module in front of it. So maybe your variable names get a little bit more verbose, but at the end of the day, you avoid naming conflicts. Okay, so kind of two things there. If we are in kernel address space here, we're going to call this shared global namespace. Bars, let's just say must have unique names. All right, so our shared global namespace must have unique names here. These are both M1 and M2, these modules would both have access to anything that's inside of this shared global namespace, as would any other program running in kernel address space. If we had some other program running over here, it probably would work through the module interface. So really we can kind of stretch this out and just say that our kernel address space is taking up all of the address space. It's not the most accurate representation, but I think it's fine for what we're doing here. All right, so these are modules that we've written for this operating system. It's plugged into the operating system through this module interface, and things that need to be shared among modules for right now, we can say, would get put into this global namespace that belongs in kernel address space. Any variable that lives in here must have a unique name. Not just variables, it could also be symbol names. That'll make sense when we get to it. Okay. So here's a simple module. Okay. Remember before I mentioned that you kind of have to follow a the rules associated with, you need to be compatible with the kernel module interface. And the kernel module interface says that you have to have an init function and you have to have an exit function. Okay, so let's just walk through well, let's read this first, then walk through the code. So my init function is the driver, this is initialization entry point, and it's called during system startup. So if the driver is statically compiled into the kernel, or when the module is inserted into the kernel. So any way you cut it, a driver is a driver. You could have a driver statically compiled into the kernel, which there are drivers that come with Linux that are part of, like last time we mentioned, there's going to be this generic VGA driver, right? That is like the most generic way to just say this video card can output to a monitor, right? And all modern video cards have to be VGA compliant, so at the very least you can get something on the screen. Well, we would assume that something like that might be compiled into the core microkernel. It is something that is required by every installation of Linux, every installation of this kernel. Okay, so whether it's compiled into the kernel or added to a running microkernel through the module interface, it's going to call this init method. Think of this as like your constructor, right, for an object. Okay, but the kernel itself, when a module gets added, will instantiate your driver, calling its constructor. Okay, so it instantiates it during system startup as all those modules get loaded in, as well as hard-coded drivers. Okay, the myExit function is the driver's exit point. It's called when unloading a module from the Linux kernel. This function has no effect if the driver is statically compiled into the kernel. Okay, because some drivers that are statically added to the kernel, they never actually unload. Where a modular driver might only load under certain circumstances, and when it unloads, under whatever circumstance, there might be some cleanup that needs to be done on exit. Okay, so these functions are declared in the Linux/module H header file. So once we get into some C stuff, we'll remind ourselves some of the header file stuff, but most of you in here had the C++ 300 class where you dealt with header files, but we'll certainly see C stuff in here. But effectively what I'm saying is if we're using the Java nomenclature of saying that it's an interface, there exists a somewhere inside of this header file a set of rules that say you have to have an init function and you have to have an exit function. All right, so the myInit and the myExit functions must have identical signatures, so they must take in nothing. Init takes in nothing and returns an int. Exit takes in nothing and returns nothing. Okay, so why are we returning then here inside of exit? Remember that the return keyword does two things. It can return a value, but it also makes a method immediately end. Makes, in this case, these are what we call functions. Makes a function immediately end. So notice this guy's not returning a value, but he is killing off this function, which you don't actually have to do. You could just let it get to the closing curly brace and be done. But a compiler, if I was writing a simple compiler, writing something for the return statement would actually be nicer than writing it for the closing curly brace. Doesn't really matter for us. Okay, so in this simple module, we look at the code. We're including a couple of things. So we're including Linux init.h. So this is initialization Linux system call stuff. and we are including module.h. Module.h is the guy that defines what all modules must have. And then we're choosing to go ahead and write my init in here that does nothing and returns 0, and my exit that does nothing and just returns. All right. Now down here, this is where the magic comes in. So it said that these two functions had to follow a certain format. That is, you can call it whatever you want. I could have called this elephant if I wanted to, but it had to take in void. It had to return an int. This guy, you can call it whatever you want, but it had to take in void. It had to return void. You had to write them to match these signatures down here. After we've written those two things, these are untapped resources at this point. That's when we then use module init, which came from module.h, as well as init.h, to pass it my init, which is a, if you had the 470 class, this is effectively a lambda expression. So in this case, it happens to be a named lambda expression. That is, the name of this lambda expression is my underscore init, and its value is a function that takes no parameters and returns an int. That's what my init is. Similarly with module exit, it's taking in a lambda expression, which is named my exit. So we have a named lambda, and it's equal to a lambda expression that takes in no parameters and returns nothing. All right. So this is the actual magic that loads a module into, that initializes the module and also sets it up for when that module would ever exit. All right, questions about what we're looking at here at the high level? Okey-dokey. All right, so let's think about what a character device is. You may have read about some of these as you were doing your paper. So in a POSIX-based operating system, which is the Linux follows the POSIX standard, so does Unix. So device files are usually stored in the /dev folder. And it's a little bit of a misleading sentence, say device files. So for instance, a printer or a monitor, something like that, any sort of device that lives in your computer, a hard drive, okay? All these devices that live inside of Linux, that live inside of that microkernel, have a file that's like your variable inside the operating system for talking about that device. So this file kind of points to, it's a placeholder for a actual physical hardware based device. All right, that's how POSIX-based operating systems do it. There exists a file for every one of your physical devices. Okay, so these guys facilitate interaction between the user space and the kernel code. All right, because we don't dive into the kernel code to directly access stuff because that would be insecure or dangerous, whatever. So we actually get the stuff through the file system. We access devices through the actual file system. If I go and look in /dev, we see that we have a whole bunch of devices in here. Let's see if video 0 is the video card. Let's see if I recognize anything else. Disk is a, yeah, so here is, notice here in the disk folder I had up here, there's multiple ways you can get at one of your hard drives. You can get by the ID of the hard drive, the partition ID, the path to it, and the user ID. So these files here, this is a link. If I do ls-la, it should show me this guy is a link that goes to this other place. All right, so this would be like your hard drive 0. Is that what that ultimately is? But for us, we don't need to worry about the inner workings of that, just that if I want to do something with a device, my gateway to talking to a device is through a file somewhere. That's probably inside of /dev. All right, so these guys facilitate interaction between user space and the kernel code. To make the kernel receiving it, to make the kernel receive anything, you can just write it to a device file to pass it to the module serving this file. Okay, so there's a middleman. We don't talk directly to kernel space. We write something to a file. The file then triggers something in the kernel, and then your driver does whatever it was going to do. The piece of software that is in charge of that on the other end does what it's going to do. Okay, so anything that's read from a device file originates from the module serving it. All right, so when you read from a file, the module, or in our case, the driver module, would be the guy that delivers the answer to what you're asking for. I.e., if we're talking about a driver for a graphics card and you're trying to do something very specific to an NVIDIA card or something like that, the software application, maybe a video game, would ask the file for the graphics card to do some kind of heavy lifting. The graphics, that file would then notify the module to do the heavy lifting and give the result back, which ultimately probably will show up on the screen. All right, but we go through this middleman so that in order for our video game over here to do something, it has to make a request from the /dev file system. So that's going to be running inside of system memory. So let me actually write it this way. All right, so this video game, let's just say it's heavily using some device that's running inside of the operating system. Its interface to that would be through this file called some device. That file actually links to a real piece of hardware that is managed by the microkernel over here in kernel address space. But notice that the video game does not get to talk directly into kernel address space. Instead, it accesses kernel address space through this file, and that file makes sure that that request goes to some module that is in charge of whether or not that's a reasonable request, a valid request, whatever. Okay, it's a checks and balances type system rather than letting this program just start traipsing around in kernel address space. Okay, so two groups of device files. We have character files. So these are non-buffered files that allow you to read and write data characters by character. So we're going to be looking at that through our device drivers. So then we have block files. These are buffered files that allow you to read and write only whole blocks of data. So let me add a little thing. Is it the next thing anyways? So a character versus a block. What's a character? When we think of the char primitive type, what are we typically thinking of as the char primitive type? I just imagine this. It's nobody has their camera on. I'm sitting here. Everybody's just online. It's just a bunch of abandoned desks. people are making lunch or whatever it is. Nobody's sitting here just talking to myself. So if we're talking about characters and operating systems, what are we talking about? What kind of animal is that?
It's a data type.
Okay, tell me more about it.
It's an 8-bit data type.
Okay, so character is a data type. Kind of depends on the language, maybe what's the size of it. But I like this idea of 8-bit because we're probably dealing with C. So character is a data type that is 8 bits in the C programming language. All right, and we're going to be using C in here. Okay, why is char 8 bits? Why do you think it's 8 bits? Is that just a made up thing? Somebody just picked the number out of the sky? Wonder why Brocker's not here today.
I'm here.
I see
I
you.
just got back from lunch, though. You know. No, I'm just kidding.
I see you on Jared's camera. So I was seeing if I could I was seeing if I could get you to jump when I mentioned your name. I work on some other classes homework. Why is it char 8 bits? What's that represent? Come on, people. You're like seniors in CS. What is ASCII?
It's like a conversion for letters and characters using a numbered value. So like 8 bits is probably the enough size to be able to record any character, letter, or anything.
Yep. So ASCII is American Standard Code for Information Interchange. It's the predecessor. So this is the predecessor. Predecessor. Did I spell that right? To what? What's the more modern version of ASCII?
Unicode.
Unicode. Predecessor to Unicode. So Unicode would require a 16-bit value, right? 65,536 unique characters in Unicode. There's only 256 unique characters in ASCII. Actually, real ASCII has 128 unique characters, but because the byte data type is the smallest data type we have, it's stored as a char, which technically supports 256 unique values, but we only use the first, well, officially, we only use the first 128 of them, although there is extended ASCII that is technically supported by C's char primitive type. All right, so a char is 8 bits because 2 to the 8th power is 255, right? Or rather 256 and 0 to 255. So it's 256 indexed 0 to 255 on the ASCII chart. And I'll go ahead and just say extended ASCII chart. You know, they added in some extra stuff, pictures and things like that. Didn't quite jump over to other languages too much, but you know, it is what it is. All right, so that's why it's 8 bits for a character. So when we write a character to one of these files, we're actually writing a byte to that file. So a block is a data type defined by the OS that we can presume is bigger than a byte. Think of this, well, actually, I'll put it in my its own section. Think of this as the difference between serial and parallel communication. Serial is one char at a time. Parallel is a burst of data at once, something along those lines. So a block would be a bigger piece of information being sent to the file at once, where a character would be a single char sent to it at once. Okay, so character files, non-buffered files that allow you to read and write data characters by character. So this is what we're going to be focused on. Block files, these are buffered files that allow you to read and write only whole blocks of data. So you're writing something, an expected larger data type, or you're reading something, maybe it's a whole string, something like that you might read from it. So Linux systems have two ways of identifying device files. Major device numbers identify modules serving device files or groups of devices. Minor device numbers identify specific devices among a group of devices specified by a major device number. We saw over here, notice we have 0, that's like, so SDA1 is, and there's an SDA0 somewhere as well. This is like first partition, second partition. So this is what the device is. This is the unique minor number of that device. Okay, so we can define these numbers in the driver code, or they can be allocated dynamically in case a number defined as a constant has already been used. The system will return an error. When a number is allocated dynamically, the function reserves the number to prevent other device files from using the same number. Okay, so that's something we talked about a little bit ago, this idea that the shared global namespace has to be unique across all modules. So we can either ask for a unique thing, or we can follow the suggestion of making sure we name our values in terms of the module that it's coming from. Okay, so here's a function to register a character device. So this is a number, so it's major revision number. This is a string, the name of the character device. And this is a struct, which is like a dictionary in Python. So a collection of name value pairs dealing with the various file operations. We'll see a real example of this. So here we specify the name and the major number of a device to register it. After that, the device and the file operation structure will be linked. If we assign 0 to the major parameter, the function will allocate a major device number on its own. If the value returned is 0, this indicates success. So if we give it a 0 here, that's saying that we're asking for it to dynamically give us a number, okay? Give us the unique number ID. That's what this int is here for. The unique number that the thing we're registering a device for has. So it'll give us like an ID for it. Think of it a social security number for this device that we're registering. So if we provide a 0 here for that, it will hand us back one that it's generated. Okay. The function will allocate the major device number of its own. The value returned is 0. This indicates success, while a negative number indicates an error. Both device numbers are specified in the 0 to 255 range. So if it gives you a 0, it worked. If it gives you a -1, it didn't work. Okay. So let's leave it there for right now. Let me just see where we're going to next. So what we'll look at next time, if you want, you can look ahead, is we're going to actually implement our first little kernel module, doing a stupid little sample driver working with a live running Linux kernel. We'll do that in class on Wednesday. questions, comments, concerns, bribes? Okay, well, hopefully I see at least some of you tonight at the 9 p.m. Hearthstone live stream right here in the same thing. So feel free to come and heckle me or whatever. Yeah, who knows? Maybe I'll suck at it, but it'll be fun to chill since we can't.
Is there a way that we can go up against you?
There is. If you have a Hearthstone account, you can certainly do that. We can. I'm trying to think. I usually you can't do it in ranked, but I can play against you in like a casual game or something. So yeah, if you play and you want to bring a deck, I'll play you live.
All right, that might be fun because I know nothing about the game. So we'll see how far I can get.
Just watch me. I just get hammered. Well, I was telling some of my students earlier, I was up early this morning because I had an early class and I was getting ready to leave for the school. And then I couldn't get my garage open because the sensors were blocked by snow or something. But I started playing and it resets at the beginning of the month. So I started off at bronze 10, like the lowest tier on the ladder. I lost like 6 straight games to, basically what presumably is like beginners, right? I was just getting destroyed. But now I've made pretty good progress. So we should be able to look at a Diamond to Legend run tonight, or at least a portion thereof.
Just got to get warmed up, right?
And maybe it was the brain thing, or maybe it was a bunch of other Legend players that were also having to reset, and I was playing against pretty good players. Because I didn't feel like I was playing incompetently. It just felt like I was losing badly. All right, I think I saw a chat. Let me make sure I look at that before I just disconnect everybody. Adam's practicing in class. All right. Well, at some point, maybe we'll play for, well, it can't be real extra credit, but we'll play for something. We'll do like first one. Usually the competition is like first one to win 3 games because there's a randomness aspect to it. So we would play until somebody wins 3 games. All right. Well, I'll see some of you tonight.
See you, Littman.